Arlington High School Math 4 Honors Lesson. I'm Kirk Weiler, and today we're going to be doing Unit number 9, Lesson number 4 on parametrically defined hyperbolas. Okay, so far we've seen the parametric equations of lines, circles, and ellipses. Today we tackle the most challenging of all, the hyperbola. Now, as a little note to students who are watching this video who aren't my students, the assumption is that you've already had a good exposure to hyperbolas. If you have never graphed hyperbolas before, if you've never seen their equations, this is not the lesson for you. We're going to review their equations a little bit and techniques, but this isn't the lesson to be introduced to hyperbolas through. Okay, so let's take a look at a hyperbola. The graph there in blue is a hyperbola. To me, hyperbolas are the trickiest of all the conics. They're much harder than ellipses or parabolas or circles, right? Because they have these kind of restricted ranges. Chunks are taken out of them. They kind of look like two parabolas. Those red lines we're going to look at immediately in the first exercise. Those red lines have a special name. They're called slant asymptotes. Really kind of cool. Slant asymptotes or slanted asymptotes. Traditionally on a graph, they're shown as dashed to contrast them with the actual hyperbola. Here I just show them in red so that you know they're not actually part of the hyperbola, but they are something that the hyperbola is approaching. It'd be kind of cool if we could zoom in out of this graph, but I can't as is. Anyhow, I'm going to just clear that out real quick, and we're going to jump right into the first problem, okay? So exercise number 1 is really a review, okay? It's a review of how to take a hyperbola that's centered at the origin and sketch its graph. Sorry, that just kind of looked a little funny there. All right. Now, please note that the reason that this is a hyperbola and not an ellipse is because of the subtraction. If we had an addition of two squared quantities, then we'd have either an ellipse or a circle. So let's review how to do this. I'm going to actually draw some axes. Well, that didn't work at all. Let's try that again. I'm going to draw some axes just using the straight lines that this program offers me. All right, let's go back. So let's review how to do this. What I'm going to do is I'm going to take this number, believe it or not, below x, and I'm going to take its square root. So that's going to be 2. And I'm going to go 2 units in both directions. Same deal here. I'm going to take the square root, which is going to be 4. And I'm going to go 4 units in these directions, in the vertical direction. Then what I'm going to do is I'm going to kind of draw what I oftentimes refer to as a magic box that uses those distances as a benchmark for how to draw it. Now what I'm going to do is I'm going to draw in the diagonal of that box. That diagonal was supposed to go through the corner and through the origin. I didn't do a very good job of it. I apologize. Those are the slant asymptotes, and I want them dashed. Or I want them a different color. I want them distinguished between that and the hyperbola. Now we know that the hyperbola is either going to kind of look like this from previous experience, or it's going to look like that. Pardon my poor drawing. So the question is which one? And what that all boils down to is whether or not the hyperbola has x-intercepts or y-intercepts. So what I'd like you to do is I'd like you to take a few minutes, you should know how to do this, and algebraically solve for the x-intercepts. Those are all locations where y is 0. And the y-intercepts, those are all locations where x is 0. So pause the video, take a few minutes, and find those. All right, let's go through them. Here we go. So x-intercepts. I'm going to set y equal to 0. All right, just follow the algebra. That's going to go away. So I'm going to get x squared divided by 4 is equal to 1. That's going to give me x squared is equal to 4, and x equals plus or minus 2. So let's be very clear. This hyperbola has 2 x-intercepts, one at 2, 0, one at negative 2, 0. I'm going to actually graph those really quick. I'm going to put them in red. There's my 2, 0. There's my negative 2, 0. Go back to blue. Let's find our y-intercepts. What we're going to do is set x equal to 0 and square it. Not that that really matters. Something like that. That term's going to be gone. It's going to give us negative y squared divided by 16 is equal to 1. That's going to give me negative y squared is equal to 16. That's going to give me y squared is equal to negative 16, and that's going to give me y equals plus or minus the square root of negative 16. And that is a problem. Not a problem as in one I want to solve, that's a problem. Right? It means that the y-intercepts are actually imaginary numbers, which means I can't plot them. Literally, I have no y-intercepts. But we can actually use that to our advantage because that means all I have are x-intercepts, and that means I can plot the hyperbola now. Oh boy, that just did not work well at all. This is not the way I want my students to graph them. I want it to come closer and closer to that asymptote. Please excuse how poorly I'm drawing. It should not cut into the box the way it did right here. That's a bad thing. It should kind of come off the box tangent and approach those asymptotes very parallel to them. Again, I'm not going to take the time to make it really look nicely, but take a look at the previous graph if you really want to see what one should look like. All right, but that's it. Now again, the assumption is you've seen this approach before. If you haven't, you probably need to find an introductory lesson on hyperbolas, not this one. Because now, after I clear the text, we're going parametric. So copy down what you need to. Here we go. All right, let's move on to the next exercise. Okay, given the curve defined parametrically by 2 times the secant of t and 4 times the tangent of t, we want to use the calculator to sketch the curve. Oh, good deal. Then we're going to use the modified Pythagorean theorem to eliminate the parameter such that the relationship is only between x and y. All right, well, hey, if we're going to use our calculator, we're going to use our calculator. Now, before we even bring the TI-84 out, please note, right, one of the issues here is that we're going to have to graph 2 times the secant of t. There is no secant command on my calculator, so I'm going to be graphing this as 2 divided by the cosine of t, and you should certainly know why that is. Anyway, let me go back to blue, and now let's bring out the TI-84. Watch this. Isn't that cool? Anyway, so now that we've got the TI-84 plus, let's do what we always do. Let's go in, make sure we're in parametric mode, hit it, and we are. Makes sense, we've been doing a lot of parametric work lately. Let's get out of there. Let's go into x equals, or y equals, sorry, and let's put in 2 divided by cosine t for our x-coordinate. Obviously clear out any equations that might be there. For y, we're going to put in 4 times the tangent of t. Okay, make sure that those are in there, right? 2 divided by cosine t and 4 times tangent t. They look good. Now, of course, the window. Let's go in there. All right, we're in our window. Let's set t min to be 0 and t max to be 2 pi, if they aren't already. Very often they are at this point because we've been doing so much work with that interval. X min, X max, Y min, Y max, you know, if you have no idea, go standard window. Let's do negative 10 to 10 for X. Let's do negative 10 to 10 for Y. We're ready to graph it. Hit graph and sit back and relax. Okay, enough relaxing. So, what we see, or what we should see, is actually the identical hyperbola to what we had before. In fact, it doesn't really make a lot of sense to sketch it, but if I was going to, right, and it's kind of hard to sketch off the calculator because it doesn't give you the slant asymptotes, right, or anything like that, but I could kind of sketch some in. And what I apparently will have is a better hyperbola than what I had before. Right? Anyway, that is actually the identical one to what we had before, and we're going to prove it right now, because we're going to use what's known as the modified Pythagorean identity to eliminate that t. Now, in the prior 2 lessons, you used this quite a bit. Cosine squared t plus sine squared t is equal to 1. That doesn't have secant and tangent in it. So very often what people will do is they'll take this identity and they'll divide each term by cosine squared t. All right, let's take a look at what happens when we do this. Obviously, this quantity is going to become 1, any quantity divided by itself except for 0. Sine squared divided by cosine squared is going to become tangent squared, and 1 divided by cosine squared is secant squared. Think about that for a minute. This is a very important identity. It is also known as the Pythagorean identity because it really contains the information that the other one did as well, although it's a lot harder to see the Pythagorean theorem in it, let's say. But how we use it, that's going to be simple, right? We can look up above and we can solve for secant. Secant t is going to be x divided by 2. Tangent t is going to be y divided by 4. So if I just substitute those in, tan t is y divided by 4 squared. Secant t, x divided by 2 squared. Let me work through this. Y squared divided by 16. X squared divided by 4. And just to verify that it's the same equation that what we had in exercise number 1, I'm going to pull everything over to this side. That's what's known as the standard form of a hyperbola. The standard form of the hyperbola always has some kind of squared quantity minus some other squared quantity, all equal to 1. When you have that, it's actually very easy then to draw your magic box, identify your center, all sorts of things like that. All right, please note that it opens horizontally around the axis that has the secant involved. We're going to keep seeing that, so I'd like to point it out right from the first time. It opens up horizontally, and it's x that contains secant. We'll analyze that a little bit more later on, but for now, just kind of see it. Okay, I'm going to clear out the text. All right, here we go. Plenty of time. Plenty of time. All right, next problem. Given the curve defined parametrically by blah, use your calculator to sketch the curve again. Yay! Then eliminate the parameter such that the relationship is only between x and y. Okay, let's do it. Let's bring out the TI-84. Let's do it this way. I don't know. I did this video just a little while ago and realized I wasn't recording volume at all, so this is my second time through. I'm going to be a little silly. All right, so anyway, let's do it. We've got the TI-84 up on the screen now. Let's go right back into y equals. Let's clear out the two equations from the last exercise. Clear, clear. All right, it's all good. Let's put in x. -3 plus 5 times the tangent of t. Enter. 2 plus 7 divided by cosine of t. Enter. Now, I'd like to go into the window right now. It could be that the window is perfectly big. I know, because I've done the problem quite a few times, that I'd like to make the y window a little bit bigger. Okay, so 0 to 2 pi is still fine for t. -10 to 10 is okay for x. What I'd like is I'd like a little bit more on y, and you'll see it for instance. I think I'm going to make y -20 to 20 for right now. Okay, so we've got it all in there. Let's hit graph. And again, sit back and relax. Okay, little map there. Nice, nice, right? Now, again, a little bit hard to sketch, let's say, because we've really just got this kind of hyperbola hanging out, right? Very hard to kind of exactly know, but let's get this out here right now. The center of this hyperbola is right there. Is at -3, 2. Okay, it's obviously very easy to tell that the hyperbola opens up vertically, just based on our calculator. Ooh, nice miss. Right? So there's our hyperbola. Very, very rough sketch. Very rough sketch. All right? We're going to figure out how to determine the magic box and all of that from here. All right? But just so that we saw it, right? It's been shifted. So now, if we want to eliminate the parameter, what we're going to do is use this identity again. It's very important to just know this identity. 1 plus tangent squared equals secant squared. Because now it's really rather easy, right? We can do a lot of this in our head. Tangent t is x plus 3 divided by 5 squared. Secant t is y minus 2 divided by 7 squared. If I do what I've done a lot of times with circles and ellipses, which is leave the x plus 3 unsquared but square the 5, same thing here, right? Then I'm getting it in a form that looks a lot more like an ellipse and a circle. Okay, And it's a good thing if I can think about it that way, because then I can understand why the center is at -3, 2. I can understand why I might go 7 units in the y direction to draw my magic box, but only 5 units in the x direction, right? It also should help me understand why it opens vertically, right? Because it's the y coordinate that's being squared before subtracting the x coordinate. Please note again that the y coordinate is the one that involves the secant function, and that's how it opens. All right, but this would be the standard form of the hyperbola in what's called implicit or Cartesian form. Okay, I'm going to clear all this out, so take a look as you need to. All right, here we go. Next exercise. Okay, well, not next exercise, let's talk. All right, parametrically defined hyperbolas. So we got our typical center. Very often we use the letters h and k, right? That always sort of begins how we write our function. All right, those that are horizontally oriented hyperbolas, ones that look like this, right? Well, they have secant in the x coordinate. Vertically oriented ones like this, well, they have secant in the y direction. Okay, so let's see how much of this we can do now without our calculators. Without the use of your calculator, sketch this hyperbola. Okay, you're going to try to get some reasonable axes on here again. And let's do it. All right, well, the first thing that I can definitely do is tell what the center is, right? The center is at 3, -1. So I'm going to go out 1, 2, 3, -1. And I'm actually going to draw in what I would kind of consider some pseudo-axes. That was supposed to go through that point. It just didn't. And that was too. Anyway, now, because I've drawn in those dashed axes, I can kind of now ignore the 3 and the -1. So now let's take a look at how we can use the 2 and the 4 to draw our magic box. The beautiful thing is no square roots now. We just simply go out 2 units along this new x-axis and go up 4 units, 1, 2, 3, 4, 1, 2, 3, 4, and that now gives us that magic box. We can now draw in our slant asymptotes. Remember, everything's dashed at this point. All right. Now the final question is, which way is it drawn? Based on the fact that you can sort of look up at that box, we could say, well, it's being drawn vertically. But let me give you another way to do it. All right, and this is very effective. Just calculate, I guess, what I would call your starting point. Figure out where you are at t = 0. Let me show you. Right, the x-coordinate would be 3 + 2 times the tangent of 0. Now, what I'm hopeful of is that you know the tangent of 0 is 0, so the x-coordinate would be 3. The y-coordinate would be -1 + 4 times the secant of 0. And again, I hope you're okay with this. The secant of 0 is 1, so I'd get -1 + 4, which would be 3. So I start at the point 3, 3. I'm going to change over to red. That's 1, 2, 3, 1, 2, 3. So there's the point I start at, right? Which pretty much means my hyperbola has to open vertically. Right? Likewise, this point would be on there. That would actually be at t = pi, but all I need is that beginning point. Really, really critical. If I have this beginning point, I can just take it from there. All right, so that's a good way to sort of eliminate having to think about the secant versus the tangent. All right, I'm going to clear out the text, so copy down what you need to. Okay, here it goes. Still plenty of time. Let's do one more exercise. So this is a nice one because here we're going to go kind of backwards. We're going to take a graph of a hyperbola and we're going to translate it back to its equation. Most of this you should be able to do on your own right now, but let's kind of walk through it little bit by little. Letter A says, determine the coordinates of the hyperbola's center. All right, so I'd like you to pause the video right now and figure out what the xy coordinates are of that red colored point. All right, let's go through it. Well, one of the beautiful things is it's just the midpoint. That's all it is. And hopefully you know the midpoint formula. All we do to find a midpoint is to average the x coordinates and average the y coordinates. So the center of this hyperbola will be at 6 divided by 2, which is 3, 4 divided by 2, which is 2. Let's be very clear. That's an x-coordinate of 3. That's a y-coordinate of 2. Simple enough. The second part of the problem asks us to find the hyperbola's vertices. Let's draw those in green. All right. I bet you can find the coordinates of the vertices quite easy, but pause the video now and try to determine what they are. All right. Let's go through it. Whoa. Anyway, simple enough. I'm going to call this point A. I'll call this point B. Point A, well, what's its y-coordinate? That's easy. Its y-coordinate is 2, right? Not just, it's got the same height as the center. But its x-coordinate, right, that's going to be 9. Point B, again, the y-coordinate is easy. It's 2. And its x-coordinate must be -3. There they are. All right, let's determine parametric equations for this. It's actually going to be pretty easy. Let's write down x equals y equals. Now, have you noticed with a line, a circle, an ellipse, and a hyperbola, they all begin with an important point. You know, for the line, it's any point that lies on the line. For the ellipse, the circle, and the hyperbola, it always starts with the center point. In other words, x equals 3, y equals 2. Plus. Now, the next number is actually sort of, if you will, the half width of the box. So, for instance, the next number for x is the distance between 3 and 9, which is 6 units. Now, there's going to be something that's going to go here, but let's just leave it alone for a minute. The y-coordinate, on the other hand, will be 2 plus this distance, right? And that's a distance of 3 times something, right? Between 2 and 5, between a y-coordinate of 2 and a y-coordinate of 5, we have a distance of 3. So now the question is, what do we put in those two things? That's where the secant and tangent stuff comes in, and it's a little bit tricky. You know, I would always advise you to check your answers. But because this opens horizontally, it's the x-coordinate that gets the secant, and it's the y-coordinate that gets the tangent. All right, so that's it. There's a parametric system that describes this hyperbola. Now, the last thing it asks us to do is come up with an implicit equation for the hyperbola. That's one that involves x's and y's, right? One equation. All right. For that, you're going to have to use that modified Pythagorean identity, so I'd like you to pause the video and try that once completely on your own. All right, let's go through it. Here we go. 1 plus tangent squared t equals secant squared t. What's tangent? Tangent will be y minus 2 divided by 3. Secant will be x minus 3 divided by 6. And technically speaking, I suppose that's an okay answer because it is an implicit equation, only involves x and y. But I'm going to rearrange it into what's called standard form. Standard form is always a good thing. All right, so I square the bottoms, leave the tops, and now I get it equal to 1. That subtraction symbol got a little bit closer to that than I wanted it to. There we go. And there's my implicit equation written in standard form, if you will. Easy to kind of see why it opens up around the horizontal, easy to see the center at 3, 2, easy to see the dimensions of the box. Okay, so make sure to check if you're ever asked to come up with the equation of a hyperbola. I'm going to clear all this out. Okay, here it goes. All right, let's finish up. This has been an interesting lesson, right? Parametrically defined hyperbolas. Tough because the hyperbolas are hard anyway, right? Difficult because you've got secant and tangent involved. That's tricky. Got to really think hard about these things, all right? But we will continue to use them here and there. For now, though, I'd like to remind you that this has been an Arlington High School Math 4 Honors lesson. I'm Kirk Weiler, and until next time, keep thinking and keep solving problems.